Another term for standardized score is z-score. And a z-score tells us how many standard deviations from the mean an observation falls and in which direction. So if you think about it, the z-score of the mean should be 0 because it tells you how many standard deviations from the mean you are. And I always kind of think of a normal curve. And this is where your mean is. It will have a z-score of 0. And we can even do some math to figure it out. For the z-score, it's x minus the mean over the standard deviation. So the observation in my data over here in my stem and leaf plot, my mean is 80. So if I'm trying to find the z-score of the mean, I'm going to use one of these 80s. The observation minus the mean over the standard deviation. And I'm going to get 0 over 6.07. And that works out to 0. The z-score of the mean should always be 0. So if you think about it, the z-score of 1 should be 1 standard deviation above the mean. So when we think of standard deviation, we want to think of 1 standard deviation above the mean. That's where 1 is going to be. So if I think about it, 1 standard deviation above the mean would be the mean plus 1 standard deviation. I should get a number about 86. I have a number 86. So this number, this observation, 86, should be 1 standard deviation above the mean. If I test it, my z-score of 86 with an average mean is 80 standard deviation. I'm getting 6 over 6.07. And I think it works out, I did this in advance, to 0.99, something like that, which is around 1 standard deviation away from the mean. And it's also a z-score of about 1.99. So if I think of it as 2 standard deviations above the mean, I would basically be taking this number and going 2 standard deviations above. So taking my 1 standard deviation and adding another standard deviation. So about 92.414. And I have a number like 93. That's pretty close to 2 standard deviations above the mean. So my z-score should work out to about 2 when I do 93, the observation minus the mean over the standard deviation. And I think this is actually in your formula sheet written out pretty clearly. And I did this in advance. It worked out to like 2.14. So this would be a z-score of about 2 standard deviations above the mean. These z-scores can also work out to being negative. So you can have a z-score of -1. And that would mean that it would be 1 standard deviation below the mean. So it would be in this general direction. We'll do more about density curves in the next and throughout this chapter, but I think I have one standard deviation below the mean. That would be 80, take away 6.07. 80 minus 6.07 brings me down to like 73.93. Something like that. So I'm looking for an observation around maybe 74, and I think I have that. So if I do the z-score for this observation, 74, take away the mean, divided by the standard deviation, I think I'm going to get -6, which is going to work out to -0.99. About 1 standard deviation below the mean, and then you get about a -1 for its z-score. So why would we want to standardize something? And I've actually put together a little chart as to why we'd even want to do this. Okay, so take a look at this little chart. These are actual statistics. Okay, we've got Babe Ruth in the year 1927. He had 60 home runs when the mean was about 7.2 and the standard deviation of the baseball players was about 9.7. Roger Maris, Mark McGwire, Barry Bonds, all similar. So a lot of people would say, well, Barry Bonds is the champion of home runs because he has the most out of everyone, okay? And maybe the reason why people are getting better and better could be because of performance-enhancing drugs or, non-illegal ones or something. So let's not get into that discussion just yet. Let's compare each one to the average at that time. The average in 1927 was about 7.2 home runs each person got on average. So Babe Ruth with 60 home runs was quite impressive. Okay, and let's compare it to Roger Maris, Mark McGwire, and Barry Bonds and see who really is the ultimate champion of home runs, if you will. So if we want to standardize each one, we want to take what their score was, their observation, and take away the mean and divide by the standard deviation. So for this one, this is going to be for Babe Ruth. And if you do some math, you get about 52.8 divided by 9.7. And I'm getting around 5.44. So that counts as like almost 5.5 standard deviations above the average. Okay, so with all things being equal right now, if we do a standardized score of Roger Maris, he had 61 when people were scoring about 18, almost 19. The standard deviation was 13.4. And I did all this math and I got 3.149. So he's about 3.1, 3.2 standard deviations above the mean. If I do Mark McGwire, 70, take away 20.7, 12.7. I got his to be around 3.88. That's better than Roger Maris. Barry Bonds. He sure seems like he would be the ultimate champion. And if you think about what these numbers represent, the mean at this time now is increased by a ton. So when it works out to his standardized score is really not, it's quite great. Because 3 standard deviations above the mean is usually where it's a very elite. Higher than 3 is very elite. If you remember that little density curve that I just did, you have the mean here, and usually all the bulk of the data is all within 3 standard deviations from the mean. So they are all up in this very elite category. But Babe Ruth is just off the chart. So you can use statistics to prove that Babe Ruth is really the ultimate champion when it comes with home runs. And that's a little bit about standardized score. We'll look into these things further as we go on.